Hello and welcome to Live from the Lab. I'm John Genke, and during this series, we're going to explore different technologies that Bruker has developed in order to help scientists understand the world around us. Today's topic, what is combustion gas and fusion analysis? And I'm joined by Okan Celik.
Hi, John.
And I guess the very first question is, what is combustion gas and fusion analysis?
Okay, it's a good question to start with. Actually, the combustion is, by definition, is the rapid oxidation of a material accompanied by heat and usually light too. So in combustion, you have three elements, actually. One is the fuel. In this case, it's the sample that you want to analyze. And the second element is oxygen, which is the carrier gas that we use in the instrument. And the third one is the heat source, which is the induction furnace that we have in the instrument. So using the combustion, we analyze carbon and sulfur content in organic solid pieces.
So basically, this is like burning wood in a campfire.
Yeah, exactly. Yeah. You burn your sample and you get carbon and sulfur out of it.
I'd imagine the temperatures then are much, much higher.
Yeah, much, much higher than that. We can go easily about 2,000 degrees Celsius.
Okay, and is that what we're looking at here? I mean, combustion, are we looking at wood? Are we looking at paper? Or what kind of samples are we looking at?
Mostly it's used for metals. It's so important for metal industry, but you can also use it for coal, coke, all other metal samples, and limestone, cement. Yeah, there are lots of different elements so you can analyze different samples.
So if I'm in a steel mill, you know, and creating this nice product, and I'm going to ship it out to a customer, why do I care how much carbon and sulfur is in that?
Yeah, as you know, carbon is so important in metals, especially in steel production. If you increase or decrease the carbon concentration in your steel, that will affect some chemical, but also some physical properties of your steel. So it can change the wear resistant, machinability, or tensile strength, and so on. There are lots of physical properties that are affected by the content of carbon. So in some steels, this carbon content can go up to 2% in steel. Or if you're analyzing cast iron, it can go even higher. But if you're analyzing high purity iron, it can also go down to single-digit ppm. That's why it's so important to be able to analyze the carbon content precisely and fast. And sulfur, on the other hand, is generally considered to be an impurity, an undesirable impurity, which will degrade the physical properties of your metal again. That's why you would like to keep an eye on the sulfur content too. And that's why we are using carbon sulfur analyzers, combustion analyzers.
So, and you also had mentioned cement. So yeah, both carbon and sulfur are important for people who are making cement also.
Yeah, that's also important. And also their fuel, it's so important. And it's so important to keep an eye on the carbon content on the. I also forgot that, but it's also important, the sulfur analysis in ore concentrations, and which can hold up to 60–70% of sulfur.
Oh, wow.
So that's one of the things that you can also analyze with these combustion analysis.
So to do a little overview on how this technique works, combustion gas analysis, Okan has brought a clip, and so we're going to switch over to that clip now.
The amount of carbon and sulfur in a material can have tremendous impact on its physical and chemical properties. Yet these elements can be very difficult to measure by direct spectroscopic methods. This is especially true when embedded in inorganic matrices such as iron and steel, cement, limestone, and glass or ceramics. But if the carbon and sulfur can be coaxed from their formidable fortresses, there may be a way to easily and accurately measure these elements. The answer? Heat, and lots of it, to the point of melting and combusting the material, forming stable combustion products. A sample of the material, chips, pieces, shavings, drillings, or powder, is weighed into a crucible and topped with a bit of accelerator. Induction furnaces use high voltage, high frequency AC power to induce an eddy current into conductive materials. The eddy current leads to joule heating, melting the sample. High frequency induction is fast, really fast. And because the sample is heated directly, it has a low thermal mass, keeping the surrounding area and components relatively cool. This allows temperatures of more than 2,000 degrees Celsius to be reached. While the sample melts, oxygen flows through the induction furnace. The carbon and sulfur in the sample react with pure oxygen, forming carbon dioxide and sulfur dioxide, which are much easier to analyze. The most effective way to detect sulfur dioxide is through UV absorption. The SO2 absorbs a portion of the ultraviolet light, resulting in a measurable drop in UV. This detection technique is much more efficient and faster than traditional IR absorption. Bruker's high sense detector is powered by a long-life UV LED source and boasts an ultra-wide linear dynamic range, staggering selectivity, a drift-free baseline, and a 10-time better signal-to-noise ratio. In much the same way that sulfur dioxide can be detected by observing its absorption of ultraviolet light, carbon dioxide can be detected using infrared light. Using a non-dispersive infrared sensor, specific wavelengths of the IR spectrum excite vibrations of the CO2 molecules in the sample gas and are absorbed. A drop in IR light is measured. Signals of CO2 and SO2 are recorded over time and integrated. Peak areas are directly related to the mass of CO2 and SO2 and is calibrated to the mass of carbon and sulfur in the sample. A fast and complete combustion is also vigorous and creates dust. Dust handling is important for analytical results, safety, and component lifetime. Improvements in equipment design have not only increased efficiency in collecting combustion gases, but they've also improved containment of the dust and debris, making cleanup faster, quieter, and more efficient, and decreasing operating costs associated with replacement of worn components inside the combustion chamber. As we push to make better, stronger materials, more efficient use of natural resources, and as environmental effects of converting and manufacturing become increasingly critical to consider, accurate and reliable measurement of sulfur and carbon become imperative to understand. Modern instruments make collecting this data clean, easy, and fast.
All right, so we got a really nice overview there of combustion gas analysis. One question that
Yes.
I have is, why use this induction furnace? Why not just heat it up with a regular furnace?
Yeah, the reason we're using induction furnace is that it can create heat instantaneously, and it can create a lot of heat. So when you're analyzing metals, you usually go about 2000 degrees Celsius, and you would like to do that as fast as possible. That's why induction furnace is the right kind of furnace to use for this
Okay.
kind of material.
So now maybe to just switch gears to this fusion analysis. How is that different than combustion?
So in
Yeah.
combustion, as we talk, and we saw in the video too, you combust you completely burn your sample, right? In the fusion analysis, you just melt your sample to extract either nitrogen, oxygen, and hydrogen, and you send those elements to the detector to detect them. And the carrier gas that we use is an inert gas. So depending on what you want to analyze, you use different inert gases like helium, argon, or nitrogen.
Okay, so combustion gas, we're going to be looking at carbon, sulfur, and we're going to use oxygen
Yes.
as the gas. And then in terms of fusion analysis, we're going to be looking at nitrogen, oxygen, and hydrogen.
Yep.
And we use an inert gas like helium.
Inert gases, yeah.
Okay.
Actually, that's why it's also called IGF, inert gas fusion analysis.
And I understand there's also a difference in the actual crucibles that we're going to be using for these.
Yeah, for the combustion analysis, we use this kind of crucibles.
Okay.
These are ceramic crucibles, and for inert gas fusion, we use this graphite crucibles, which sits on top of the lower electrode. And on top of the crucible, we have the upper electrode. So an electrical current passes through this graphite crucible. And so depending on the application, we can go above 1000 amps. And it heats up instantaneously the graphite crucible. And then the sample is dropped in the hot graphite crucible, and it melts, and it releases those gases.
So this one, we have this inert ceramic.
Yeah.
And we're going to heat that up with the eddy currents interacting with the material
That's
inside.
right.
Whereas with the graphite crucible itself becomes the heater.
Yes, exactly. That's how it works.
Okay. And because it's made of graphite, that's carbon, then we don't do the carbon analysis with that.
Yeah, exactly. That carbon comes from the graphite crucible.
Okay. So I think it's time to see some of these techniques in action. So we're going to head on over to the lab, and we'll see you there. So here we are in the combustion gas and fusion analysis lab. This machine, it says the Icarus.
Yes.
So which kind is this? Is this the combustion gas or is this the fusion?
So this is a combustion analyzer to
Okay.
detect carbon and sulfur in solid pieces. Yeah.
And it looks like, I guess the first thing that pops out to me are these tubes.
Yeah, we
What
have
are those?
some
What's that going on?
chemicals on the front side.
Yep.
This white one that you see is magnesium perchloride. This is for removal of moisture that
Okay.
you may have in the sample, especially if you're analyzing more samples. And this one is sodium hydroxide to eliminate the CO2.
Okay. So basically that's the intake. That's where the air from the room is coming in.
Yeah, actually, this is for pre-cleaning of the carrier gas.
Okay, carrier
And
gas.
yeah, this is for the moisture removal from the sample.
Okay, so those are the kind of the inputs, and that's going to come here. This
Yeah.
looks like the business end.
Exactly. This is the furnace.
Okay.
In here, we have the furnace, and above this, inside this box, we have the auto cleaner. I'm
Mhm.
going to open the furnace now. This is the crucible carrier that we
Okay.
have. So if you want, you can go ahead and analyze the sample.
Yeah, that's great.
And
Let's
we can
see it
talk
in
about
action.
the
So it looks like you've
analysis.
kind of preloaded this. You've weighed it
Yeah,
out.
in this ceramic crucible, we already have the sample, and on top of the sample, we have the tungsten accelerator. So yeah, I put it on the crucible carrier, and I start the analysis.
Okay. So now you've mentioned an accelerator.
Yeah.
So what's the role of this accelerator material?
So basically, accelerator is used to create the heat that we need to burn the sample. So once the high frequency induction furnace is turned on, it will create an alternating electromagnetic field, which couples with that accelerator, and that accelerator start heating instantaneously. That's why we get the heat that we need. And now it's switched on. The combustion has just started. So you can actually see the combustion through that small window.
And I see this coil. That's that induction coil?
Yeah, that's the induction coil.
Okay.
Correct.
And it's basically burning off all
It-
of those, the carbon and the sulfur.
Yeah, it's burning off the sample, and CO2 and SO2 are swept by the carrier gas, the
Mhm.
pure oxygen, and they go to first the UV detector for
Okay.
sulfur analysis, and then it goes into an infrared detector for carbon analysis.
So it looks like here on the screen then, we see a few peaks that have popped up.
Yeah, here on the screen, we have this gray peak, which is the carbon content, and this small peak, the orange color, is for sulfur. In a few seconds, the analysis will be completed, and we will see the concentration of carbon and sulfur on the screen. There we go.
So
So-
basically, end to end, we're just talking a few minutes.
Yeah,
get those
typically less than a minute.
Mhm.
It's pretty fast.
So if I was in the cement industry, in the steel industry, this would be an analysis that I'd really want to do quickly so that I
Yeah.
knew if I have to adjust parameters.
Yes, yeah, that's what you have to do. So you
Okay.
you can use different type of accelerants, different settings in the software, depending on what you want to analyze. And this is the go-to method for carbon and sulfur analysis, because in those industries that you just told, you need to be fast and efficient.
Okay. And now how would I actually get the sample? Like, so do I have to grind it? Do I use machining?
So if it's in powder form, you can directly put it in the crucible, no
Okay.
problem. Or if it's some small chips or drillings, you can also put it, or small pieces, small pins, you can also use it. But if it's a big chunk, then you would probably have to drill it to get some sample out of it.
Okay, so if we have, say, if I'm in a foundry and we have a machining operation that happens, I could actually take some of those, the shavings, and then
Yeah,
I could
shavings, tarnish.
clean them thoroughly.
Yep.
Use those directly.
Yeah, correct.
Okay, great. So now this was combustion gas, carbon, sulfur.
Yes.
Now we also mentioned fusion analysis
Mhm.
for oxygen, nitrogen, hydrogen. So
Yep.
is that
So
one
if
of
you want
these?
to analyze oxygen and nitrogen,
Yep.
and also hydrogen, then you will need a fusion analyzer. This is the G6 Leonardo. This particular unit is configured to analyze oxygen and nitrogen only. It can be configured to analyze either a single element or double element. So again, in this one, just like we talked in the studio, we have the graphite crucible here. So once we start the analysis, this will go up, and it will start the current, and it will heat up the graphite crucible.
Okay.
So here I have a small sample.
So you're going to put that into the crucible?
I will put it in this funnel here.
Ah, okay. So it actually
Okay.
goes up here to start with.
Exactly. So let's open this so you can see what's inside. And here we have the sample loop. So I will start the analysis now. And the crucible carrier will go up. And the As you can see, it will go up.
That's loading it up into this little chamber zone.
Yeah, when the time comes, that loop will rotate and will drop the sample into the hot crucible.
Okay.
So
So right now it's heating up. It's
heating up the
dispersing.
crucible, yeah, it's using the carrier gas. In this case, we are using helium. So it will outgas the graphite crucible, and then it will also check the baseline if you have a stable baseline. And if everything is okay, when the time comes, it will drop the sample into the hot crucible. It will melt instantaneously, and it will release those gases.
Okay.
Oxygen will form CO because the carbon comes from the graphite crucible, and nitrogen is released as the molecular nitrogen N2.
Okay.
And then that CO goes to the infrared detector for oxygen determination, and then nitrogen goes to the TCD, thermal conductivity detector.
Okay. And then from a safety perspective, once those gases have reacted, we've measured them and such, how do you exhaust that? Does that go out a vent or something?
Yeah, there's an outlet at the back. If
Okay.
you want, yeah, with a hose, you can just use a fume extractor or something.
Okay.
Or if you have a line in the building, you can also connect it so it will be exhausted.
So kind of like if you had a fume hood hooked up or something.
Yeah.
That's the type
Yeah,
of
yeah.
setup that you'd use. All right. And
So
so it looks, I can actually see some light going on in there.
yeah, if you're seeing light, it means that it's already
Nice and hot?
yeah, it's hot
Yeah.
and it's glowing. So in a
Just
few,
getting ready to, we're going to see a twist, and then on here we're going to see the.
yeah, you will see that the sample will rotate and will drop the sample in the hot crucible, and in a few seconds we should be able to
Okay.
see the peaks on the.
And in this case,
Yes.
what was the sample? It looked like a little metal chunk,
It's a small steel sample.
Yep.
Yep.
just like a pin
Okay.
almost, huh? Okay, yeah, I just saw it rotate. So I'm
Yeah.
guessing that was it. Popping
Now
in,
it's in the crucible and
Okay.
it's already melted. Actually,
melted.
in a few seconds, actually it's already started. Here on the screen, you can see the blue line.
Yep.
This peak is the oxygen peak, and a few seconds later will come the nitrogen peak, which is in green. Okay, there we go. And the second peak, here we see, is the nitrogen peak.
Okay. And sort of like we saw in the video about combustion gas, we create a calibration curve for the
Yeah.
peak areas here, and that's how it tells us how much.
Yes, exactly. So you use some certified reference materials and you calibrate your method. First, you need to set up your method with all the parameters, and then you have to calibrate it. Once it's ready, just like here, you just drop your sample in there and you're good to go.
Now, this instrument, the G6, this is capable of measuring 2 elements. But if I wanted to measure 3, I wanted to measure nitrogen, oxygen, and hydrogen, then I'd have to step it up to a little
Yes,
bit
in
different.
that case, you would have to use another fusion analyzer like the G8 Galileo.
Okay.
So the difference between the G8 Galileo and the G6 Leonardo is that G8 Galileo can have 3 different elements: oxygen, nitrogen, and hydrogen in one single instrument. And some other features that we can have on the Galileo is that we have a crucible changer, automatic crucible changer, automatic cleaner, and also on top of it, you can also have the optional auto sampler, which can hold up to 40 samples. So these are the main differences, but it's also possible to hook up a mass spectrometer to the G8 Galileo, which is important because if you want to analyze argon inclusion, let's say, in additive manufacturing, it's a big issue. So in that case, you can just hook up a mass spectrometer and analyze it.
And I've heard that that's actually one of these environmental factors is, can we reuse the powder of additive manufacturing? And a lot of that concern is the argon inclusion that you
Yeah,
mentioned, right?
that's what they do. They reuse, and but that also changed the oxygen content, for example.
Okay.
And that's one of the main applications actually for fusion.
Really? So
Yeah.
this kind of is supporting that coming industry that we all know is going to take over manufacturing, a lot of manufacturing, right? What is there any other application? And so is this also used in the steel industry, or?
Yes, it is.
Okay.
It is. Almost every steel manufacturer has this kind of instruments, fusion analyzers.
Okay. And now there's this topic I've heard of before. There's hydrogen and then total, and then there's diffusible hydrogen, especially when you're welding. Right?
Yes, diffusible hydrogen, we can also do that. We have a dedicated diffusible hydrogen analyzer, which
Yep.
is called G4 Phoenix, but it's also possible to analyze the diffusible hydrogen with the G8 Galileo if we have the optional IR07 infrared furnace.
Okay.
So with the diffusible hydrogen, if you have a welding seam, for example, you will probably have some diffusible hydrogen in it. And it's so important because this diffusible hydrogen may cause hydrogen-induced cracking, and it's a big issue. So just after the production of a metal or just after the welding, you would like to put the sample in the infrared furnace and analyze that diffusible hydrogen. But you have to do it just after the production because by the nature of this diffusible hydrogen, if you just put it here on your desk, that diffusible hydrogen will come out of the sample with in less than 72 hours, actually.
Okay, and so my understanding then is like when I'm welding, and I'm going to try to use a blanket gas in order to protect that weld, but sometimes what can happen is that some hydrogen gets incorporated too.
Yes.
And some of it is in that form of H2, which is kind of more stable, but that
yeah, it can be in the hydride form, stable hydride form, but you will also have some diffusible hydrogen, definitely. And if you want to analyze that welding seam, for example, later on, what you can do just after the welding, you can put it in liquid nitrogen and freeze it, and that's how you store the diffusible hydrogen inside your material, and then you take it out and put it in the machine.
So having access to a machine like this, it's important because then what we can do is kind of create a test specimen while we're welding the major part, run right over to the lab, stick it in, and then know we're good to go.
It's crucial.
Okay. So that was really nice overview of these different techniques. What we're going to do now is head back to the studio and answer some of the questions that have come in. All right, so we are back in the studio here to answer some of the questions. If you have any questions that don't happen to get answered during the stream today, make sure to email them to live.events@broker.com. And also, by the way, if you like what you're seeing here, if you like this stream and you want to see it keep going on, make sure that you like, subscribe, and share it with all of your friends. So the first question that has come in is from William. And that question is, are these methods standardless? Or do I need to be able to create a accurate calibration curve with known samples due to matrix effects?
Okay, that's a very good question, William. So these are not standardless methods. So you will have to calibrate your method, and you can use CRMs for oxygen, nitrogen, and total hydrogen, and also for carbon sulfur. There are lots of CRMs available in the market in the form of powders, drillings, chips, etc. You can use those to calibrate your method. And this kind of analysis, fusion and combustion analysis, these analyses are free of matrix effects because what you do at the end of the day, you extract those elements out of your sample and you analyze them in dedicated detectors. So matrix effects are not in play here. And by the diffusible hydrogen, for the diffusible hydrogen, you have to have an instrument like the Galileo, because in the Galileo we have this gas dosing unit. What it basically does is to inject some calibration gas into the TCD to calibrate it, because there are no diffusible hydrogen standards available in the market.
So you just kind of use these generic standards that have a known amount of, say, carbon, sulfur in them, and then whether that's a steel, whether that's concrete that you want to measure, you can go with those. Okay. So actually, there is a follow-up question from William related to that. And is it possible to detect carbon in a non-conductive sample like salt?
Yeah, actually, you can do that. And we analyze that kind of samples too, some salt samples. It doesn't have to be conductive because is that carbon analysis? Can you go back to the question, please? Okay. Carbon, because what we do is that we use the accelerator, and what creates the heat is the combination of accelerated and the high-frequency induction furnace. So it doesn't matter if it's conductive or not, because the heat will be created by the accelerator.
Okay. So the next question, that's from Daniela. And how do I know when to change the chemicals? Now, I'm guessing that they mean those Daniela. And how do I know when to change the chemicals? Now, I'm guessing that they mean those tubes that were sitting in the front.
Yeah, that tubes that we saw in front of the instrument. So for those chemicals, you should keep an eye on the color of those chemicals. For example, for sodium hydroxide on support, which is the black chemical that we saw in the lab. So it will change its color from black to grayish color. So it's a good indicator that you should change that chemical. On the other hand, for magnesium perchlorate that removes the moisture, you will see that it will get wet in time. But in metal industry, it will not happen so quickly due to the very low levels of moisture. On the other hand, if you're analyzing some ore samples, you will see that it will get wet pretty quick. So this is how you say that you should. It's a good time to change the chemicals.
All right, so the next question came in through the stream by Karen is what kind of sample prep is needed for CFA? I'm guessing she meant both combustion gas and fusion analysis. So what do we have to do to prep?
For the sample prep, like we talked in the lab, if it's a being of metal, so with the drillings, you can get some samples out of it. And if you're concerned that it's not completely clean, you can clean it. And other than that, if the sample is in the powder form or some small chips and or drillings, you can directly put them in the crucible. Other than that, there's not much to do about the sample prep.
So can I use a solid chunk?
Yes, you can.
In both methods?
Yes, you can do that.
Yeah.
Well, it depends on the sample size. In both inert gas fusion and combustion analysis, the typical sample weight is less than 1 gram, approximately. So you would like to keep your sample weight below that.
So now I know with the fusion machines, we put the sample in that top funnel.
Yeah.
Could I use a powder in there, or does it have to be a solid piece?
If you want to analyze powder, you have to put this in small capsules that we use. You put the powder in the small capsule, and you seal it, and you put the capsule in there.
Okay.
That's how we analyze.
So the next question is from Abdullah. Is it possible to measure ONH on other materials? I'm guessing they're probably asking not just steels and say cement, but plastics or...
And other materials, we can also analyze in some other materials. Titanium, for example, it's an important application. Copper also. There are lots of different metal alloys that we analyze oxygen, nitrogen, hydrogen in them.
All right. And then another question from Karen. How does the surface area of your sample affect the results, in particular oxygen?
Okay, that's a very, very good question, Karen. Thank you for asking that. So it's so important when you analyze oxygen, you should keep an eye on the surface oxidation, because if there's surface oxidation on the sample, it will increase your results. So what you can do is by etching, you can try to remove that surface oxidation, or you can just, with some kind of treatment, you can also try to clean that surface oxidation so that you can get the real oxygen concentration in your sample. Otherwise, your oxygen content will be much higher.
So in your experience, how much of an effect is this? If I have some fresh drilling, if I take a sample, right then maybe I do a pre-drill, wipe away the surface stuff, and then I drill a little bit deeper, take that sample, walk to the machine, dump it in. Am I good to go?
Yeah, you're good to go. If it's a fresh sample, you will not see that effect.
But if it's been sitting kind of in a humid environment for a few days,
it will get oxidized, definitely.
Okay. So the next question from Fabio, what do we need to take care of to analyze oxygen and copper? And that's actually a big thing. I know when I walk to the electronics store stuff, they have these wires and they say, oh, it's oxygen-free copper, therefore it's better, and it'll make my TV sound better.
What type of, can you go back to
oxygen and copper.
Oxygen and copper. It's a very nice application, actually. You don't have to go higher temperatures. Around 1500, 1600 degrees Celsius would be enough. And for the copper, you don't have to do much. You just put it in the sample funnel. Once it's dropped, you can easily analyze the copper. But again, the oxygen oxidation, surface oxidation might be a problem. Just be aware of that. But other than that, copper, oxygen in copper is a pretty standard and easy application. And the good thing is, we know that these crucibles are generally not reusable. But with the copper application, which is an exception, you can reuse the same crucible again and again up to a few times. Because due to surface tension, after the diffusion, you will get a small ball of copper, which looks pretty nice, actually.
So we might have to try that sometime. Maybe I'll grab one of those oxygen-free wires, and
Of
we'll
course.
chop it up and then see exactly if it meets the spec on the wire.
Yeah, definitely.
So we've run out of time today. Again, if you do have any additional questions, please email them to live.events@brooker.com. And until next time, make sure to keep your signal high and your background low.